Hello everyone, I'm Charles Clark. I'm a physicist at the National Institute of Standards and Technology in Gaithersburg, Maryland. I work full-time at the Joint Quantum Institute on the campus of the University of Maryland in College Park. You can read more about me at my online CV, which you can find at the link in the center of the page. And I'll certainly be happy to meet any of you, any admitted or entering graduate student. Just make an appointment. For the near future, it's going to have to be a virtual meeting, but that's nothing new right now. And just if you want to meet, just contact me at cwc@umd.edu to find a mutually convenient time. The theme of my research, put simply, is transduction, the conversion of signals between physical systems. This is a modality that we use to detect things, or to interrogate them, or to control them, or to transfer functionality between different physical systems. The platforms that I use are neutrons, light, and atoms. What is a neutron? Well, it's amazing. It's the only nucleus that has no electric charge, and so it can go through matter with the greatest of ease. Here's an example of that. You see these two flowers on the left-hand image, two flowers in a lead bucket. This is a cask that's used to transport radioactive materials, seen from above with a photograph with a mobile phone camera. Now from the side, you see a neutron radiograph. What's happened here is you imagine you take the image on the left and rotate it 90 degrees into the page. So you're now looking at the side of the bucket. Well, behind the bucket is a source of neutrons, the neutrons from a nuclear reactor. And the neutrons come right through the lead, they scatter from the flowers, they go through the lead again, and then they're detected by a neutron camera. And do you see, you can see the vein within a leaf of a flower inside the lead cask. You can see the stamens and the pistils inside the delicate blossom of this flower, encased in a lead environment. This shows that the coherence of neutron sources survives passage through dense matter. They are unique in that respect. Now, my main efforts in neutron imaging are associated with neutron interferometry, which is pursued at the NIST Center for Neutron Research. That's a nuclear reactor in Gaithersburg, Maryland, and it's unique in the United States in having a neutron interferometer, which I guess if you look in the figure in the center, is very similar to the Mach-Zehnder interferometer, optical Mach-Zehnder interferometer, with which you may be familiar. And here's some samples of recent work done in collaboration with a group at the Institute for Quantum Computing at the University of Waterloo in Ontario, Canada. Generation detection of spin orbit coupled neutron beams. This is a first effort in trying to get general control of the phase of the neutron wavefront so that one can enrich neutron scattering investigations. We've done the analog of holography with a neutron interferometry, with a neutron interferometer, and our first steps in this direction were stimulated by the amazing recent work that's been done in putting optical angular momentum, putting orbital angular momentum on photons, on beams of electrons and other things, X-rays, and we found how to do that in neutrons, and it's sort of been a main direction of my research in recent years. Optics learns from neutrons. So here's an example, cover image on Physical Review Letters of November 2018. This lattice image that you see is one that we were designing for use by neutron beams, but we found that we could implement it as a proof of principle with a laser system, and this gives a new way of making spin orbit coupled optical lattices. In another sort of engagement between neutron and light, I'm involved in a project on developing a new optical scintillation neutron detector, very lightweight, using silicon photomultipliers to replace high voltage gaseous electronic systems, and NASA has picked this program up as a promising vehicle for developing a neutron detector that could find water on rocky planetary bodies like the Moon and Mars. Another interaction of light and matter, this characteristic of my research, two main branches. One is looking at excitations, electronic excitations, organic and inorganic color centers. This is work done joint with Yu Huang Wang in the Department of Chemistry at the University of Maryland. And then ultra-cold atom superfluids, basically applied Bose-Einstein condensation with a focus on the so-called atomtronics, making circuits of ultra-cold atoms. And I've worked with a number of the experimental groups in this field over the years, and most recently with Gretchen Campbell, my NIST colleague, who's also at the Joint Quantum Institute. I'll end where I began, except to say that physics and chemical physics are very demanding academic subjects. No one applies to them frivolously, thinking they'll just kind of cruise through and have a holiday for a few years. So if you've been accepted by our program, you're the best of the best. And we can make you even better if you join us. So I do hope you'll strongly consider enrolling at the University of Maryland. And if I can be of any help, and on a confidential or broadly informative basis, not just to sell you on my program, but to tell you what I know of the things that might best be suited for you, please feel free to email me and arrange for an appointment. In any event, I hope to see you enter the program this coming autumn. Stay healthy. Hope to see you soon.